like to welcome you to the Create Science Seminar. I think is this the first one we've had this semester?
The first one.
Wow, it seems, yeah, it's been a long time. Okay, so I have a few announcements and then I'll introduce our speaker. So the first announcement is that after Stacey's presentation, it says Dr. Bretz here, but I stumbled on that. There's time allotted for graduate students and postdocs, so I hope that you will take the time to meet with her and maybe eat some more. And the next speaker is actually in 2 weeks, I think, Cindy Mello Silva from Indiana University. And those, I think, are the only two this semester, I think. All right, so it's my pleasure and honor to introduce Stacey Lowery Bretz from Miami University in Ohio, and the Miami University. I've known Stacey for a very long time. I first met her when she was a graduate student and I was a mere young assistant professor at a Gordon conference, and I met her because we were sitting there, everybody very quiet, and this irate voice from the back row said, "Do you have any evidence for that?" and she's continued with that, asking for evidence ever since, and we've been good friends for a long time. So she started at Cornell University, she postdoced at Berkeley, and she's moved around to her now present elevated chaired professor position in the chemistry department at Miami. So without further ado, I would like to introduce Stacey Lowery Bretz.
My thanks to Melanie for the very kind and professional. When you go somewhere and get introduced by somebody you've known for a couple decades, you sort of worry that the introduction may take a left turn to photographs that we're not supposed to be seeing, and we actually have mutually assured destruction video of each other riding a bucking bull. So thank you for the kind and professional introduction. Okay, so I'm actually very happy to be here. I've had great conversations all day so long, and I'm looking forward to talking to the grad students and postdocs some more afterwards. Can I just I want to get a sense of who's in the room. So how many of you would identify as a chemist? Okay, biologist, physicist, engineer, computer science, mathematician. Okay, what haven't I called it? We got everybody?
Science educator.
Science educator. You're good. See, you're so part of all of them, you cross all of them in my mind. All right. All right, so how long ago, for those of you who do not identify as chemists, how long ago was your last chemistry lab experience in years?
Can we switch that to decades?
Decades? I'm a chemist. We're all good with unit conversions. I can do that easily. What do you got? How long ago was it?
15 years.
15 years? Anybody never taken chemistry lab since high school? High school was the last time? Excellent. All right. So I'm going to talk to you about our efforts to understand what's going on when undergraduates enter the chemistry laboratory. In my previous life as a bench chemist, I was an analytical chemist, so I worried about measurement greatly. And how do we think about the precision and accuracy of the measurements that we're making. Okay, so yeah, I should have asked this. How many people in the room are administrators? Control over budget? One? Okay, so switch back to your faculty hat for a minute. Shut off your administrator here. Okay. So I don't know about your institution, but my institution is constantly worrying as a public state university about the budget situation and the governor's defunding of public education. I'm on our university's fiscal oversight for the University Budget Committee, and that is like a whole world of hurt no faculty member should ever know about. The sausage that goes into making a university budget. So administrators are constantly looking for ways to save money, and from time to time they'll do things like wander over to the bookstore and make lists of who's got the most expensive textbook and who charges the highest fees, and we have a budget model where they can actually calculate how much FTE income I bring in as a professor and how much it costs to pay me my salary, my benefits, the space in the lab. And they could literally figure out, one person at a time, your net drag or influx into the university. And places like Texas A&M have actually published these spreadsheets for faculty. So this is not a, I see some dropping jaws amongst the grad students and postdocs. And this is not a hypothetical question. One thing they'd have to come up with is chemistry lab instruction. It's incredibly expensive. It's specialized space that once it's turned into a laboratory can almost never be renovated for anything but laboratory space because you've spent all the money plumbing utilities in there. You've got hoods. You have waste that's generated, in part because not everybody has a green curriculum. You have waste that's generated because students are learning and make mistakes. You have to dispose of the waste. We have a teaching model that puts graduate students in these laboratories, and graduate students come with the cost of stipends and tuition waivers. So administrators will wonder things like, couldn't we just do virtual labs? Couldn't we just run this with simulations? What evidence do you have, chemists, although you could insert your own discipline there, that your laboratory experiences are essential to student learning? What evidence do you have that this matters? Now the initial response most chemists have is, of course we have to have a lab. You can't possibly be a chemist without having good hands. You can't, well, there's a few theoreticians who like to just think, but most of us have to have good hands in the lab. It's essentially, you can't imagine it. And yet, the evidence that we have, or the lack thereof, is pretty shocking. So, there have been many reviews in the literature written about what do we know about learning in the laboratory, not just in chemistry, but broadly across science education. It's just assumed to be important. There's actually little evidence to justify that. We haven't been able to draw simple connected dots between what a student learns in lab that they can't learn elsewhere. And this report, which is actually from the Australian Council of Deans of Science, is wondering whether we need a laboratory program at all. So when you see deans start to talk like this is when faculty need to step up and go, we need to do something about this. We can't assume it's always going to be there just because we say it's important. So I had the pleasure of serving with Melanie on the NRC panel that wrote the Deber report. We were the two, well, there were three chemists on the panel, but we were the two people in CER in the panel. And we didn't find much either. One of our tasks was to conduct a synthesis of the literature across the 6 different disciplines that were represented in this report. And there's very little, whether we're talking about laboratory-like chemistry, field work in biology, field work in geology, there's very, very little that we can point to as evidence of student learning. And so one of the things we said in the report was, part of the problem is we don't have anything to measure with, and part of the problem is we maybe need to think about things beyond just hands-on skills the students are learning to broaden our conception of what learning in the laboratory might be. So I'm going to show you some work that I've been doing actually for the last 10 years. The beginnings of it were largely a collaboration with Marcy Towns, who's at Purdue University. And if I had to represent it, how chemists like to think of lab, this is how we think it works. We have some things we want to have happen. We come up with experiments that, of course, make those things happen. Students come in and they learn. That's how we think it's going to happen. And so over the last 10 years, Marcy and I have been trying to think about how do we characterize these gears, if you will, and what evidence can we collect to show the extent to which this model is operational. So at the beginning, Marcy and I spent a long amount of time interviewing faculty who had funding to improve their laboratory curriculum or facilities in chemistry, and we compared those to faculty whose department had not had funding, who were just maintaining the status quo. And we wrote a series of papers about how faculty view the lab, what should be the goals, how do they talk about this, and then Marcy's group actually turned those qualitative studies into a national survey where they collected data from chemistry faculty across the country. This slide always makes me laugh because the original grant, I'm aware that the IU's deadline is today, the original grant proposal that we wrote was 3 years for CCLI. We said, in the first year, we're going to talk to the faculty, and then the second year, we're going to talk to the students, and then the third year, we'll just fix it. Straight up, that was our proposal. And we got a call from the program officer and said, you know, your proposal reviewed really well, but we think you might need a little more time. And that was new to us. Never has NSF called us back up and said, you need more time, you need more money. It's usually, we want to fund you, but you have to cut 10% of your budget. And so this 3-year plan has turned into now over a decade of research. So I guess NSF knew best that day. So this slide is meant to give you a sense of what the faculty told us. There were goals in common for faculty, focused on skills and techniques, critical thinking, whatever that means to them, and experimental design. And then you have some, depending on the first year, second year, or upper division laboratories, some other things that show up according to chemists. So for example, upper division physical and analytical labs are very much worried about error propagation and uncertainty in measurement. But not so much teamwork. That was something more that people were working on in first years. We also did some work characterizing that second cog in the wheel, the curriculum. Okay, so we worked to develop a rubric where we could say how many degrees of freedom does a student have in carrying out this experiment, designing the experiment, deciding how they're going to analyze their data, represent or communicate their data. And so we did this both within chemistry and across STEM disciplines. And I want to show you a slide here that has a table, the classic slide that says, I don't intend you to read this. This is our rubric that moves across different levels and different elements of design in a laboratory experience. But in general, it moves from left to right, from more choices already made on behalf of the student to the student having more degrees of freedom to make their own choices about how to explore it. And when we applied this rubric to the different disciplines, astronomy, biology, chemistry, geology, meteorology, physical science, and physics, we took lab manuals and programs that self-identified as inquiry. And these are the levels, and you don't need to read the numbers to see that most of the data points are in the more choices made for students and not in the students get to do their, to have more degrees of freedom. And so we looked at over nearly 400 experiments across these. So it's not just chemistry that's in this boat. This is a pedagogy that pervades much of how undergraduate science is taught. So we looked at faculty goals and curriculum, and then I've spent the last 6 or so years looking at, well, what do the students tell us they're experiencing in lab? And that's what I'm going to share with you today. So the theory that shapes how we look at all of this is from Ausubel and Novak's Human Constructivism, where the idea is that learning requires students to have experiences. Those can be cognitive, affective, or psychomotor. Meaningful learning only happens when all three of those are integrated. This is a bit uncomfortable concept for a chemist because we tend to think about chemistry as thinking and doing, and that affect has, you can't have affect and be a scientist. There's no crying in chemistry. Well, there is. We see it around drop days in general chemistry, sadly. But chemists tend to think of their role as teachers and what students need to do as learners to being stripped of affect. And one of the things I've been trying to say as I go around and present my research is we actually have molecular level evidence. This is to our own detriment, right? So if you conduct functional MRI studies, one of my favorite papers is from MathEd, where they took children who had high math anxiety and low math anxiety, and they put them in the functional MRI, and you can actually see the amygdala processing differently during simple math tests, right? And the amygdala is sort of the gatekeeper to the rest of the brain. All intellectual processing happens after the emotional processing happens first. And so if the fear factor is high, things are not going to go in for processing, or they're going to go in jumbled because of the fear factor. If the fear factor is low and people have a positive affect towards what they're learning, then that can facilitate making connections, because meaning only comes when you integrate the thinking, the feeling, and the doing. So doing is pretty obvious in the laboratory, but how do you measure what students are thinking in the lab? How do you measure what they're feeling? That is not so easily observable. I'm just gonna take one moment. I need to blow my nose, I'm sorry. It was 80 degrees where I was yesterday, and it's about 20 degrees cooler up here today. So, okay. So we asked some pretty broad questions as we set off to see how this theory could shape and inform our understanding of what's happening in an undergraduate chemistry laboratory. We wanted to know, what do students have to say about their cognitive and their affective experiences? How do those experiences compare to what they expected when they showed up? Okay? And how do these change as students learn more chemistry? So these are pretty broad, and I'm going to share with you, I think we've now published about 7 or 8 different studies about this. So I'm going to share with you a subset of the data. So the way we went about developing this measurement tool was we did the quantitative piece first and then the qualitative piece afterwards in our mixed method study. So we developed an instrument that I'm going to introduce to you here, and then we observed students in the lab. We had them wear GoPro cameras so that we could see what they were seeing, what they were, and as they were talking about their laboratory experiment. And we did this both locally at Miami, and then we did a cross-section study nationally, and then we also had the opportunity to try to do a longitudinal study locally. Okay, so these are some screenshots that we get from students on the GoPro cameras. I'm not going to talk about the qualitative data. That would be a whole separate talk today, but you see some really, well, you confirm things that you remember when the last time you were a laboratory instructor, like students scraping their sample off the counter and putting it in, or picking it up off the floor, or saying things like, is this in the right place? I don't know. What is this thing? I don't know. We're just told not to touch it to the bottom of the beaker. They forget that they're on camera very, very quickly, and so you get a very honest picture about the mechanics with which they approach their experience in the laboratory. The idea is to get in, get out, make as few mistakes as possible. Don't let the TA know you've made a mistake if you've made one. And make sure that whatever you're doing looks exactly like the person next to you, because that's how you're going to know you haven't made any mistakes, independent of an assessment of the quality of the person's thinking and doing next to you. So, yeah, this is just a whole fascinating thing. So basically what we did with these, I will tell you what we did. I just don't have time to talk about all the findings. We would then bring students in within 24 hours after they've done this and say, tell me about a time you felt you were learning yesterday in lab. And we would find that part in the film and talk with them, have them narrate what they were thinking as they were doing things. And they would say, tell us about a time that you were really confused in lab. And we'd find that. Sometimes students would say they didn't really feel there was a time when they were learning, so we talked only about the confusion part. Yeah, I understand the laughter. I share that, but remember where my talk started? Like, we're in serious trouble here with the money. So I am going to talk with you about our quantitative results. So we developed something that we called MILI, Meaningful Learning in the Laboratory Instrument, and MILI is designed to be given as a pre-test and a post-test. So before students, when they're checking in, we ask them to respond to these items, and the items are worded about what they expect to have be part of their learning when they're in the laboratory, and then the same items are given to them after they've completed the last experiment of the semester, and we just change the verb tense to this be in the past to reflect this did or did not happen. We want to characterize their experiences. And then we look at the alignment or lack thereof between these two. So MILI has 3 different scales on it. There's cognitive items. So here's some examples of that. They have to make a decision. Some of them are negatively worded as well, right? So we reverse code those. There's affective items. And then there's some items that have both a cognitive and affective component to it. We tried to write items when we originally did this that were purely psychomotor, just the doing, and we found as chemists we could no longer do that. It's possible students could give us items that were very just psychomotor, but anytime we tried to write something about a doing, we had a thinking component or a feeling component about it. So Millie ended up with C, A, and C/A items. And then there was one item to check that students were reading the actual instrument as they were taking it. And then what we did is on each of these, we averaged a student's response to give a composite score for this scale. So the responses take the form of percent agreement to one of these items. Okay, so you can do this on paper. We tend to do it in Qualtrics because the students, actually we did a validity study, we get the same quality either way, but students enjoy the interactiveness of answering this, so then they'll click it and drag it out. And if they want to say they completely disagree with something, then they have to drag it out and drag it back. You can't just not respond to the item. So this is what the interface looks like. They tell us the percent that they agree with the statement. These are worded in the pretest. I expect to learn chemistry that will be useful in my life. So then on the post-test, this would say, I learned chemistry that is useful in my life. Okay? So we worry about the structure of our instruments, to be sure. So one way to examine the internal consistency, not the only way, but one way is to look at the Cronbach alpha. And in the literature, there's traditionally a cutoff of 0.7. So you'll see there's some numbers up here that are less than 0.7. Cronbach alpha has been horribly abused in science education research. You can artificially inflate it just by adding redundant items and then watch the correlation go up. That's great. It's better used for measures of affect where people have an opinion or an attitude towards an object. It's less useful in a cognitive situation because it measures the internal consistency, and so you expect to, when you're asking students to think about something where there are holes in their knowledge, errors in their knowledge, connections that are there that shouldn't be there, connections missing, and then you try to say how well these items are aligned, you're going to get a lower alpha simply because it reflects the incoherent nature of students' cognitive structure, not because your instrument is poor. So you have to take alphas with a large grain of salt anytime you look at them. And the way we go about interpreting these is that within the cognitive and the affective, there's a good deal of internal consistency. It goes down. We attribute that more to students' experiences not matching their expectations than the items didn't change their structure. And the reason that the C/A is lower is because these are not integrated in the students' minds, not because the items are internally inconsistent. Okay? All right, so let me show you some data here. The first study I'm going to talk about is one where we just did this at Miami with a pre and a post test where we had the fall laboratory course in between. Second, the national sample, where we did that with a factor about 10 times bigger for N. And then I'm going to show you what happened in the longitudinal study at Miami, where we tracked them. They took this 6 times from the pre-test, post-test at the fall, post-post in the spring, came back to organic, took it as a post-test at the end of the fall, and then post-post at the end of the second year. Okay, so here's what some data looks like. Students expect to consider if their data makes sense. This is not a mass spectrometry plot or something like that. It's good. Laughing at the chemistry jokes is always good. We see the spikes at the 10. That's an artifact. We know of them dragging the clicker bar out. We make no claims about the precision of measuring an 88% agreement versus an 89% agreement. But you get a general sense here that students, yeah, they expect to be asked to do this as part of their college laboratory experience. And if you look in general chemistry versus organic chemistry students, there's really not any difference there. They both have this expectation. Do they expect to feel intimidated? You see that this looks very different as an item. And so you start to think, well, okay, this is probably the general chemistry students who are nervous. They haven't taken college laboratory before. They're worried about it. The OChem students have been through it before. They're done here. That's not what we saw. We saw a spread from general chemistry. When you talk to the students in an interview, this is very much a reflection of their prior knowledge, what sort of laboratory program they did or did not have in a secondary setting. Shapes that, so this does not concern us at all, but the organic chemists are actually worried about being intimidated, yet they signed up for more. right? So they're about to go through our lab for the second time. So that's disconcerting that students expect to feel this way when they've already completed 1 year of college laboratory. Let me show you some comparisons here about expectations and experiences. So they expect to learn chemistry that will be useful in their life. Majority more, yes, there is a spread. This is what they tell us, that they learned chemistry that was useful in their life. When we look at that, we wonder, well, who shifted where? Clearly the bottom picture is not what we would like to see in terms of a post comparison to a pre. So if you make a scatter plot of pre on the x-axis and post on the y, you can see that almost all our data points are below the y equals x. Now, this is two-dimensional plot, so we don't have the third dimension of what the n is for each circle coming out at you here, but we know that most students' expectations went unfulfilled. Okay? That laboratory, whatever it's for, is not about teaching them something that's going to be useful in their life. And when we interview students, we thought, well, maybe they mean like life outside of school, life with grandma on the weekends, camping or something like that. And they're not thinking about life as their future career. But they talk about their life to include their future career, and they just don't think chemistry lab will have any role in that. I expect to think about what the molecules are doing. This is the core of a chemist's heart. I thought about what the molecules were doing. So, how do you explain that? This falls on assessment, right? Well, they're not going to spontaneously think about the molecules, except the rare person who's truly meant to be a chemist. But assessment is the tool that we can use to get them to do this, and if we're not asking them to do this, this is why they tell us, no, this is not happening. So we created these composite scores for students, and most of the graphs I'm going to show you here, they all have pre on the x-axis, post on the y. This is what the cognitive averages look like for the students in general chemistry. This is the affective pre-post, and this is the C/A for their experiences versus expectations. And then we have it for the organic chemistry sample as well. So some observations about this data. There's definitely more spread in the affective than there is in the cognitive, and the C/A turns out to always be in between those. So the way that we've come to think about these after talking to the students is the university selects based on cognitive prior knowledge. I'm in a highly selective, primarily undergraduate institution. The average ACT score is now 29 for us. So there's not a lot of variation in students who are taking first year college chemistry in terms of their cognitive background. These are STEM majors, so this includes chemistry majors. It also includes all our life science majors, our engineers, et cetera. We don't select on affective responses. We don't have it. I'm not saying that we should. And so it's not, we're not surprised by the larger scatter in the data there. Okay? And you can see for the organic situation, one thing I hear my colleagues say is that Gen Chem's a weed out course. Now, I detest that term. I don't view my role as somebody who teaches general chemistry nearly every semester. My job is not to weed out. But a lot of faculty take pride in that approach to their introductory science. And so the rationale for weeding out is only those who should go on do. But the experiences of the organic students who persist are not more positive than the students who are reporting to us in general chemistry their experiences, right? We still, look at this affect for the organic students. This is quite, I have not taught organic lab in probably 20 years, but this concerns me greatly that it's down there. Okay, so we wondered, how are individual students changing? I mean, the scatter plot tells us a little bit about this, but we created these things, we call them vector plots. We hadn't really ever seen them before, but we wanted to get a sense of what were the biggest changes going on in our set. And so what we have here is cognitive on the x-axis and affective on the y. Okay? And we took the students who had the highest 5% cognitive averages at the end. So the people who had the most positive outcomes cognitively at the end, where did they start? Okay, so their post is in this red and the pre is in the blue. And so when you look at that, you can see that it's not like they all started down here and had these large gains, right? The direction and the magnitude of the vectors, there's some variety in there. But let's compare that to the people who had the bottom 5% of the cognitive experiences. What we found interesting about this plot is that I think it's all too easy as an instructor to say the students who do the worst started out down here to begin with. They didn't want to be in lab, they're not capable of thinking this way. This is what feeds into that weed out mentality that we have. And if you look at this, the blue is pre, right? These people had the lowest cognitive experiences, but look where they started with their expectations. They came with an open mind. They came reporting that they expect to be able to do these things, or to be asked to do these things, and they're saying it just didn't happen. This is the same idea, but for the top affective averages. Okay, so the blue pre on the top affective post, and here's the bottom affect. Right? These people came in with some reasonably positive emotions or attitudes about chemistry, and they walked away with those just destroyed. Okay? I worry a lot about the number of majors that we lose, how many people are changing from chemistry to something else, how many people are changing out of STEM altogether because they're having such negative affective experiences. Okay, so this vector analysis that we did suggested to us that there would be different groups of students in our data that we might want to look at. And so, I don't know, about the time that we were doing this, I heard a talk at a conference on cluster analysis, and I said, hey, we should use this on our data. So cluster analysis, of course, is the complete antithesis. It's orthogonal to factor analysis. Factor analysis is all about how do these items hang together. Cluster analysis is all about how do these people hang together. And that's far more interesting. For all the reasons I said that Chromebook Alpha is troubling, it's more interesting to look at the groups of people you have, because then you can think about designing pedagogical interventions for different groups of people. So there are many ways to do cluster analysis. We did one that's called hierarchical agglomerative, which basically means if I have 400 students in my pool, I start with each of them in their own cluster of one. So I have 400 dimensional space. And then I used a squared Euclidean distance measure to find the students who are most like each other, and they cluster into a group. So now I have 399 groups. 398 of one group of two. And so that iterates over and over, and once you've joined a group, you can't unjoin it to become another one. And the variables that we used to do our cluster analysis were the students' cognitive and affective composite averages for both pre and post. Okay? So here's some results we found in this first study at just Miami. There are 4 clusters in here. It may not look like it from this scatter plot, but I'll show you. This is the cognitive pre-post, and here's the affective pre-post. This is how we know that there are 4 clusters in here. There's a lot of measures you can calculate to convince yourself it's 3 versus 4 versus 5. I'm not going to go into those, but in the affect, you can clearly see that there are students who come in with low expectations, and we affirm them. They don't expect this to happen, and it doesn't happen. Now, that may or may not be a good thing, depending on what the task is. There's students who have high expectations, and those are affirmed. And you might think, well, this is good. But if this expectation is, I'm only supposed to focus on the procedure and not think about concepts, and they say, yep, that's what happened, that's not a good thing for us. So it's not as simple as, did your experiences match your expectations? Because buried in there is, does this item contribute to meaningful learning or detract from meaningful learning? So we have the low, medium, high groups, and then we have this purple group here, which we call the change group, because they come in with the same, on average, expectations as the high group, but they report experiences that are very different. They change in a way that the green group doesn't. And then the C/A group is in all of our data in between these two scenarios. Okay, so as I've said, we tried to think about it this way in a 2x2. Did they expect it? Did it happen? But we soon realized that was not going to lead us to a meaningful analysis of what was going on with each cluster. So we changed to some other displays here, and we made these box plots for the different clusters. So 1, 2, 3, 4 is low, middle, high change. Okay? And I have the pre in blue and the post in green. So here's an item that asked them to feel, I expect to feel unsure about the purpose of the procedures. And yep, that's what happened. And you can see for each of the clusters, right, a slight uptick in what happens. But for the change cluster, there's a very big difference. I expect to be nervous about making mistakes. Our low cluster agrees very strongly with that item, right? They have high fear factor. It declines as we get to the high. Here's the change group who was, yeah, no, I'm not terribly nervous about this. Oh boy, I got worse as the semester went on. So what's going on in there instructionally, pedagogically, from an assessment point of view, that's making students be more and more nervous about making mistakes? I will tell you from our GoPro footage and interviewing these students, one of the factors that contributes to this is that we don't allow for time to make mistakes, and furthermore, we penalize for making mistakes. I don't know any scientist whose experiment has worked perfectly the first time they tried to make something. It's never happened in the lab. It doesn't happen. Learning from your mistakes is the hallmark of doing science. Why didn't that work? Why did I get different results? What am I going to change? How am I going to analyze my data differently? The science keeps repeating itself, waiting for us, the human, to figure it out. But when we teach students science, we design an experiment that takes all 3 hours. They're all supposed to do exactly the same thing. I'm speaking in gross generalizations now. I realize there are different places that do things differently, correctly. We design an experiment for all 3 hours, no time to make a mistake. The grading rubric penalizes you for making mistakes. You get a lower percent error, or you can't identify your unknown correctly. You lose points there. So the message we're sending to students is, if you can't do this perfectly the first time out, maybe you don't belong here. Related to that is their confidence in the laboratory. And you can see that all the students, they're on the other side of 50, right? They expect to come in and develop confidence. That's why they're going to take this course. They're going to learn how to do this and be better at doing it. And all of them report a decline in the change, the biggest. You've seen this item before, but now I'm breaking it out by clusters. So it's not as though our high-performing group actually is the only one thinking about molecules. They're saying they're not asked to do that as well. Okay, so once we learned this locally, we thought, well, the curriculum at Miami, lab is a separate course. I would say it's pretty traditional, despite the fact that it bills itself as inquiry, and I have data to prove that from the rubric that we've looked at. We wanted to know what was going on across the country. So we did a national data collection from a wide variety of schools. These are the complete data sets that we got. And I'm going to show you some data from this. When we collected the data, we got students' responses to the Millie. We had faculty take the goals survey that Marcy Towns' group developed from our extensive interview projects. And we had them send us their curriculum so we could analyze it with the rubric. So massive data set. Here's what we got for Gen Chem 1. So I know there's a lot on here. I've provided the numbers if that's what you like to look at, or have the graphs if that's better for you. I prefer the top half. We were shocked. It's 2,800 students, but we were shocked to see the same pattern emerge nationally. We thought for sure. We know we're looking at places with different kinds of curriculum. They're getting different scores on the rubric. How is it that students can still be having such a common experience here? So clustering, that's not the word I want to use, clustering of the clusters, that's what I was about to say. There's not much differentiation here cognitively, but affectively this big spread was going on. And you still have this group. Like, so what happens to them when they say my experiences don't match up to my expectations? Do they persist? Are they leaving? That was a question that we wondered from that. This is the organic chemistry. Now this is a cross-sectional study, right? Like, so we're not longitudinally following students. This is data collected all at once. What's different about these than the Gen Chem? How many clusters are here? There's just 3. That change cluster's gone. So we wondered, well, where did they go? Did they just not take organic chemistry? Did those who persisted somehow get recalibrated by their experiences and change their expectations? Well, I've had a year of college chemistry laboratory. This is how it goes. Apparently I had the wrong expectations coming in, but now I know how this works. And so did they get subsumed into one of the low, middle, high groups? So we wanted to do a longitudinal study. It's very difficult to get funding to do a longitudinal study. NSF is, budgets from the White House don't come out with longitudinal plans that often last long enough to do a longitudinal study. But these are the hallmarks, right? You've got to follow human beings to see what difference is really happening at the level of an individual. Cross-sectional studies can only get you so far. And of course, the Deaver committee was prescient enough to say, this has got to happen, right? So we did this even though we didn't have funding for it. I took some money from my endowed chair and said, we're just gonna make this happen because I want to see where that 4th cluster go. I was determined to come up with an answer to that. So here's what we did. I've already shown you this before, 6 data points in time. We followed the same human beings. This is difficult to do because this requires the cooperation of multiple faculty colleagues to measure students in their course, and some colleagues are more willing to facilitate anything you'd like to study, and some are concerned about what are you going to do with the data. You're going to use it to say I'm a bad teacher. So we lost signal as we went along, to be sure. We ended up with 268 students who answered it at least once in each year. And we found 61 human beings who had answered it all 6 times and that we could match the data on. Right? That's the other thing longitudinally. One of these days I'm going to get a functional MRI like attached in the office next door, and I'm just going to have a high throughput sampler where students just go in and, right? That's my chemist dream, right? We have auto samplers for everything else. We're just going to have an auto sampler for, no. Well, and I recently just read something that there's an error in the algorithm that processes the data from the functional MRIs, and now over 40 studies are up in the air about do we really know what we know. But I digress. Okay. This is what it looks like for cognitive, for affective, for these 61 human beings. So we did a power analysis. We actually only needed 20 people to be able to follow this through. They're still here. This change group is still here in our longitudinal group, even though they were not there in the national data we had for organic chemistry. When we did a repeated measures ANOVA, so our between groups variable was which cluster they were in, and our within groups variable was time, right? And so here are the 6 data points along the time, and the residuals for each of the 4 clusters. We found something very interesting that was happening. So before Gen Chem, after Gen Chem 1, at the end of the first year, organic 1. There's this reset that's happening for our students where things went downhill the whole first year, but they come back the second semester, the fall, like, it's gonna be better this time. It's gonna be better, and then it's not. I find this compelling data. Here's the affect, and here's the C/A. I find this compelling data because I think it's all too easy as an instructor, whether you're faculty or laboratory GA, to blame the students. They're not succeeding in lab because they're not interested in it. They're not succeeding in lab because they don't understand what it means to do experimental science. The data we got from all of these studies suggests to us that's not true. There's a mismatch between what we say we want lab to do as faculty and what experiences we craft for students to engage in. So we have been undertaking from that NASA data set, trying to triangulate the faculty goal survey with an analysis of their experiments and their students' Millie responses. I had 2 undergraduates work on this for over a year, and I have to tell you that the Venn diagram is no overlap, essentially, between these. There's what faculty say they want to have happen. That's not evident in their laboratory curriculum, and therefore, not surprisingly, the students' experiences don't affirm those goals. So then we turn to, well, let's give the faculty the Millie. Because one of the problems we had was we couldn't match items on this goal survey to items on the Millie. This is an interesting methodological problem because the items on the goal survey were all grounded in years and years of interview data. The faceability of these items was very high. These are very authentic things that faculty resonate with. The Millie is all grounded in theory about how human beings learn. And there was no overlap between those items. That tells you something in and of itself about how chemists think about learning. So in order to compare this, we needed to have signal on the same instrument because the 2 instruments were not converging in any way for us. So we tried to do a census study. We contacted every department chair at an ACS undergraduate approved program. There's 677 of those across the United States. And we invited them to give us the names and email addresses of anybody that teaches Gen Chem or OChem lab for them. Okay. We got a 21% response rate from department chairs, and we invited 685 laboratory instructors to take the Millie, and we got a third of them to respond. Okay. This gives you a sense of who those responses were. So the middle here is how the highest degree distributes amongst those institutions. So we didn't just have all doctoral institutions or all just undergrad. And this is our responses from Gen Chem instructors and our responses from OChem instructors. So we feel like we got a cross-section of the possible instructional environments for chemistry. I just want to, this analysis is ongoing. We're going to have this for San Francisco in the spring for ACS. I just want to show you some preliminary information here. This is not published yet. So there's some good things here. You hope that students felt intimidated. The faculty, no, they're not out to hurt the students. That was nice to see affirmed, right? That's not what you see there? You guys are having a great response to that. Yeah, who are these outliers? Yeah, right. Yeah, there's some. Right. So then you wonder about these human beings and you go and look at their actual individual responses and it's like, okay, it's a good thing that there's an IRB. So my graduate students de-identify the data and then I look at it, so I was really happy because if I had actually known who that person was, probably would have had, right, these people are scary as all get out. This is what the Gen Chem instructors say, this is what the OChem instructors say, and we ask them this, how they want their students to answer on the post. Like, what do they want to see their students say when the course is over? And this is what the students say, right? They do feel intimidated by Gen Chem and OChem. You saw that data before. We asked the Gen Chem and OChem faculty, do they want students to make decisions about what data to collect? And of course, the faculty are like, yeah, of course. But when we're looking at the rubric analysis of their curriculum, that degree of freedom is largely missing for students. Do you want your students to think about what the molecules are doing? Again, these outliers are a little, like, well, who are you? Who gave you your PhD and why are you allowed to teach somewhere? These are things that trouble me. As I said, we're still analyzing this data. I want the students to use observations to understand the behavior of atoms and molecules. Yes, we want them to do that, except for a few organic chemists. And Yeah, so faculty, here's the upside of the faculty Millie responses. They seem to have reasonable expectations for what they want their students to experiences, but the students are telling us it's not happened. There is one, we're still teasing apart, where I want the procedures to be simple to do. Faculty don't agree on that. And if you start to think about what that means, some faculty want that to be simple to do. Why? Because you don't want to have extra waste in the lab. You're trying to make sure the experiment works for everybody. And other people are like, no, I don't want it to be simple to do. I want them to understand that there's choices to be made, complexity and measurement, etc. Okay, so some conclusions we can draw at this point from the work. These were the research questions I started with. High cognitive expectations for laboratory exist in many groups of students, and they go largely unfulfilled for them. Most students view the purpose of laboratory as a means to measure how well they can follow the instructions. Right? Our grading schemes reinforce that. Students are highly aware that they can go through lab without thinking about what they're doing. That's not required. It does seem as though there are groups of students whose expectations are closely tied to their experiences. We see these clusters, right? Affect seems to be an opportunity to change this, right? So the cognitive data is tightly clustered together, but there's a wide range of affect, and it seems like we ought to be able to design pedagogy and change assessment to try to move those students with lower affective experiences higher. And curiously, students are willing to reset their resilient, right? So even if what happens to them their first year is not good, there is an opportunity not to be squandered in the second year because they come back with a reset expectation despite the fact that it didn't happen in their first year. And cluster analysis has turned out to be a very useful tool for us to think about the different groups of students that are in our lab. So what are the implications here? First of all, faculty and students need to talk about affect. Faculty need to get on board that affect is part of learning. It's shaping learning. Sometimes it can enhance it. Sometimes it can impede it. That needs to be happening. Curriculum should incorporate affective dimensions explicitly, including through the assessment. Students cannot be expected to engage if they don't expect them to happen. So when a student says to you, well, I don't expect to think about what the molecules are going to be doing, even if the case where the assessment tools provoke and prompt that kind of thinking, that's a barrier they set up from the beginning. About they don't understand necessarily the structure of the discipline, and that's okay, they're a first-year student. But unless we make those assumptions explicit about why we designed the course and how we designed the course, help them have some meta experiences about their learning, then that can impede their experiences as well. Learning theory is far more useful way to do this than just asking faculty what they want to have happen because they turned out to be chemists. So I need to thank all the students who graciously shared their thoughts, quite honestly, no matter how painful they were for us to hear. The faculty who also shared their views on teaching. Teaching is a very personal experience. I know we've had some nervous laughter, but unless people are willing to honestly say, this is why I do what I do, I didn't know it could be done any differently or it could be any better, we're never going to be able to improve it. Most of this work was done by Kelly Rush Galloway, who actually started as an REU student with Melanie and then came to be my doctoral student, and now she's a postdoc at University of Ottawa with Allison Flynn. And Joanna and Elizabeth are the undergrads trying to do the triangulation with faculty data. Michael's a high school teacher in Kentucky, and he and Nathan did the work on the curriculum initially. I need to acknowledge my colleague Ellen because for many reasons, but we have, for one, we have joint group meetings, and everything in my students' work is always better because Ellen has improved it. Marcy and her students for their work on the Faculty Goals Project, the generous support of NSF, and the Volweiler family at Miami, and you for your attention. So I'd be happy to answer any questions.
I'm not sure exactly. So if a student APs out of general chemistry, I don't know, it must work differently at lots of different universities, but don't some students then start in organic? Basically, I'm wondering if you ever thought about or thought not to parse the organic students by those for whom it really was their first experience in college, their first laboratory experience in college, what it wasn't?
So I will tell you, we did not specifically collect that demographic. I think that does matter, or vary widely by institution. So at my own institution, we have lots of students who have 5s on AP. We have a governor who says if you have a 3, you have to give them credit for something. So what we've done locally is the students who get 5s, we encourage them not to take organic chemistry first, but to actually take an honors majors lab where they get hands-on access to all the research instrumentation directly. So they're doing a completely different set of experiments and running HPLCs and GCs and mass specs so that we can not have them go directly into organic. Right.
Yeah, that's how it worked at Illinois too, and I was just curious, I didn't know if that was common or not common.
So, but in the national data set, I also don't have gender data. I don't have any theory that points to me that women would have a different cognitive or affective, but you could explore gender as well if you wanted to do that. Yeah.
Yeah, great talk.
Thank you.
And kind of building off that, I guess you just remind me of the talking about leaving. So what about DFW rates and what about for your own institute? Do you have demographic data that talks about how these things might be implicated in?
Right. So that's a great question. There are some complicating factors. So at my institution, lab and lecture are 2 different courses. So who's in which lab section is actually a hodgepodge of across the lecture sections. So there's been some hesitation to ask that information for fear that I would try to peg it on a particular colleague doing different things. I can tell you that the DFW rate at my university when I was first hired was 30 to 40% from the general chemistry lecture. I was there 2 weeks and I was hauled over to the provost's office and told I needed to fix it. And I respectfully pointed out to the provost that I had not caused it. I'd only been there 2 weeks. And he said, didn't we just hire you to like do this chemistry education thing? And I was like, yes. And he said, well, fix it. In particular, he was concerned if you looked at, so students take first year biology and first year chemistry from the get-go at Miami together simultaneously, and it was a particularly toxic combination if you looked at the DFW rate for students co-enrolled in both of those courses, and it was even worse for underrepresented students in those courses. So we actually took the students who scored the lowest on our university math placement test. So Miami gives a math placement test. It's just 25 multiple choice. I solved it once on an airplane. The person next to me was a little nervous. I was having fun. I hadn't factored things in a while. I was like, oh, I remember how to do trig. Okay. So if you plot that math placement score versus graded Gen Chem, not surprisingly, there's a very nice correlation, or poor correlation, depending on how you look at it. And we took the lowest students and we pulled them aside and we added an hour recitation for them. We did not have recitation hours for the rest of the students. And what I did in that recitation was we did POGIL activities, scale-up guided inquiry activities with them to introduce new materials. Everybody had recitation on Thursday. And then at the end of that hour, they generated questions they had on their mind. And I used those questions to frame lecture on Friday, Monday, Wednesday. And then we had another guided activity on Thursday. And the DFW, so we took all the students who DFW and we put them in my class. Somewhere about 2 weeks into the semester, I had a panic attack and I went to the chair and I was like, everybody who drops is in my class. I could have no students. And he's like, well, you can't let that happen. I said, but you understand, they're all in my class. I could have no students. He says, well, don't let that happen. So I'm very pleased to say that we had, in the 3 years I taught that course, I had 5 students, 3 students, and 4 students out of over 200 drop, or withdraw, just W. It means I kept everybody else. And when we gave them the ACS General Chemistry exam, we were only 3 questions lower than the mean of the students who had the higher math placement scores. So there are ways to deal with learning chemistry that don't require the plug and chug math mentality. You can focus on generating questions, building models. I know I'm preaching to the choir here, but and we were able to generate DFW data to show that we had made a difference.
Okay, good. Is the DFW data at all connected with the affective data that you have?
No, those are two separate
Okay.
studies separated by about 5 years in time, yeah.
Okay, so unfortunately, I have been told that there is another class scheduled in here that I didn't realize about. But I'm sure Stacey would be happy to answer questions if we went down to create and you're going down there for.
Sure,
meet with
I'm
the
happy,
students.
I'm here all day.
Do apologize. So please join me.
That really was a great talk.
Thank you.
Yeah, 'cause I'm not on your schedule. But
Hi. Thank you. Thank you.
I did once have the experience of, so, you know, we have two tracks in organic. We have sort of the majors track and the pre-med track, so to speak.
What is your discipline again?
Organic.
Organic, okay.
So I actually asked the class at the beginning of, I was teaching the pre-med track. I said, how many people do